So today we'll be talking about sequences, and I think like this point right here, this video in this material is what I think of as a turning point in Calculus 2. I think you'll find that with this topic and what comes after it, that the math gets a little easier, but the concepts get a little more difficult. All right. So, in other words, when you're doing integrals, integration by parts, trig substitution, those problems can take a lot of work. Like the math is somewhat complicated. Here, that's not really true for the most part, but it's going to take you learning some new notation, some new vocabulary, and some new ideas, and that's what can be difficult, all right? But good news is I don't think the math is that hard. All right, so what's a sequence? A sequence is an ordered list of numbers. It's not just a list of numbers, it's a list of numbers in some definite order, okay? Now everybody knows what a list is, and everybody knows what numbers are, and you know what it means to be ordered, so it's probably not that hard to understand what a sequence is. Let's look at an example. The Fibonacci sequence is a well-known sequence. It can be given by description right here. The first two terms are 1, and all other terms are the sum of the previous two terms. And the Fibonacci sequence, by that description, would look like this. The first term is 1, the second term is 1, the third term is 2. And if every other term is the sum of the two terms that came before it, it would look like this, all right? This list of numbers in that order fits that description that was given up there as the Fibonacci sequence, okay? All right, so notice that there's no end to this thing. It's only that if you're a mortal, you have to stop writing it at some point, okay? The sequence goes on forever. So we put these three dots when we're done writing some definite number of terms of a sequence, and those are called ellipses, and they just indicate that the sequence continues forever, all right? Okay, so yes, there's nothing that stops this sequence besides me having to quit writing it at some point. And that will be true for all sequences that we see. So, very important, notation. If you open a math book, you'll see lots of symbols. You'll see words, but you'll see lots of symbols. That's called notation. Part of math is learning the notation, all right? You gotta know what the symbols mean. When we write A with like a subscript, that indicates a specific term of a sequence. So A with a subscript of 4 is the fourth term of the sequence. Well, so first term, second term, third term, fourth term of that sequence was 3. So A, we would write A subscript 4 is 3. A subscript 7, the seventh term, well, so it's 13 up there. We also write things like A with a subscript of n. What would that mean? The nth term. I guess somebody's going to have to tell us what n is for us to know what the nth term should be. But we do write that sometimes. And I guess in that context, if I wrote A subscript n minus 1, doesn't the number n minus 1 come before the number n? Wouldn't that be the term before this one? Okay, just as an idea. All right, sure, that's what it would mean. So that's our primary notation for sequences, is just to give symbols that represent terms of the sequence. All right, so let's try something a little bit different then. Take this idea a little further. So if I give you a formula, say like this, so write the first 4 terms of this sequence. That's a formula to get the terms. You tell me what n is, and I can do the math over here, and I get that term, all right? So this formula will give term n of the sequence. It will give the nth term. So how do you think that you use this? It's probably not hard for a person to figure out how we would use this. If you want the first term of the sequence given by that formula, you let n be 1. You get this. You do the math. First term is 1. Second term, you let n be 2. In that formula, you do the math, you get 4. And you keep going. Third term, let n be 3. You'll get 16. Fourth term, let n be 4. you'll get 64. Okay, and then dot, dot, dot. There are the ellipses again, telling me that the sequence goes on forever like that. But just so that you could get an idea about it, I wrote the first 4 terms. It's not hard to use a formula like that. It really isn't. Okay? All right. What about one like this? Okay? This is called a recursive sequence. And the reason why is that if I think about what that says, it defines terms from the ones that came before. All right? So we can read it like this. So it says a sub n is 3 times a sub n minus 1 plus 1. That's what it says. But remember, a sub n is term n. A sub n minus 1, well, that's the term that came before term n. So I can read it this way. Like in English, I can say any term is 3 times the previous term, then plus 1. That's what that says if you translate it into English, all right? So yes, those are recursive sequences. Anytime that we define terms from the ones that came before, it's recursive. So here's the way that this one works. The first term is given to be 2. I've got to give you one of the terms. How are you going to figure out the others if you don't have, say, the first term? You find the second term from the first term, so you need to know at least one of them. If I didn't give you this part, there's no way that you could use that and actually figure out what the terms are. So say we want to find the second term. All right, it was given that the first term is 2 and any other term is 3 times the term that came before it, then add 1. So I could just do that. I could just do the math. But I should show people how that you actually use the formula and plug the numbers in. How are you going to use this to find the second term? Well, I'd let n be 2, right? Why would letting n be 2 find me the second term? Well, if I put 2 for the n, look what it says. It says a subscript 2 is 3a. What's 2 minus 1? Okay, 1 plus 1. So the second term is 3 times the first term, then plus 1. All right, well, the first term's 2, right? So what's 3 times 2 plus 1? That will be 7. So that's how you can use this to find the term you want. You make the subscript say what you want it to say. If you want the third term, you put 3 for n in this statement, in that formula, and it will tell you the third term. It will say the third term is 3 times the second term plus 1. Well, so that would be 22. All right. And the fourth term is 3 times the third term plus 1. Well, that would be 67. All right. But I could, that's the way I think about it. I just think about it like that. I read it. But, you can plug the formula if you want to. Just let n be whatever you need it to be. All right. Okay, so that's a recursive sequence. Let's see another one that might be a little bit more involved in that one. Okay. All right. So let's see. Here's another recursive sequence. Now, for the subscript there, we can use n, or we can use k, or, we could use any letter of the alphabet. I guess n and k are the most common. So here I decided for the subscript for the terms, I'll let it be k. It doesn't really matter. Now, this is recursive because it says, like, any term is defined from the 2 terms that come before it, squared and added together. That's what that says. Like, because say you got term a sub k plus 2. Now, I don't know what k plus 2 is until we give k. But what's k plus 1? Isn't that right before k plus 2? That's right before it. That's the term right before it. And then what's k? Isn't that right before this one? So that's 2 terms before that one. So for example, say k was 5. This is 3. Okay? This is 4. Or sorry. Say k was 5. I started with, that's 7. That's 6. That's 5. Term 7, term 6, term 5. You see? It's define any term from the two terms that came before it. So I give you the first and second. Can you find some of the others? Here's what it would look like. The first term is 2. The second term is 4. What's the third term? How would you use this to get the third term? Well, you can read it and you can say, well, the third term is the second term squared plus the first term squared. That's what it says. But if I wanted to be more direct about it for you, I could say, look, here's how you find the third term. What number can I put in for k that would make this be a 3? Because if I could do that, it would tell me the third term is, and I would do the math over here. So that would be 1. I would need to put 1 for k, right? That's what's going to make that be a 3. So if I put a 1 for k, it's going to say a subscript 3, right? 1 plus 2 is 3, isn't it? All right. And then that says what? A2. And then that says what? A1. So I was right, wasn't I? This says the third term is the second term squared plus the first term squared. So in my case, well, the second term is 4. And the first term is 2. So, okay, that's going to be 16 plus 4. So that's 20, right? Okay. So what's going to be the term after that? Well, you would find the fourth term by letting k be 2, right? But it's, just try to verbalize the formula. That's really what I recommend. See if you can read it to yourself. See if that makes it easier. I mean, what that formula says is that term would be these two terms that came before it squared and added together. If you take 4 squared plus 20 squared, you'll get 416. And then it continues forever. There's the ellipses again. Okay, so hopefully I talked a little bit about everything with these. You can use the formula directly to find whatever term that you want, or you could just think of the meaning of that and just calculate directly that way, okay? All right, so I think that's the ways you can look at a recursive sequence. Now let's find some deeper patterns in sequences. So say I give you this sequence right here. 2 times n over n plus 1. That's the formula. That will give you the nth term, all right? Now I want to find some patterns, and I want you to be able to find some patterns, all right? And these patterns are very specific that I'm looking for. So let's say I've got the formula. I can write the terms, all right? First term is, well, how would you find the first term? You put 1 for n. It's 2 over 2, so that's 1. How do you find the second term? You put 2 for n. That's 4/3. All right, you get the idea. There's the numbers. That's the sequence. So if you don't see a pattern to that, maybe we can do this. Maybe we can get our calculator, and then we can maybe round these out to decimals or something, and then plot each number, right? So like if the first term is 1, when n is 1, an, the term is 1. If the second term is 4/3, that's about 1.3, then the second term puts me here. There, I put it at about 1.3. You see the idea? Okay, that's if you wanted to visualize it. That's what the terms look like, okay? Now, you may not see a pattern here. It's a little more obvious that you see a pattern right here, okay? So yes, I hope that when I say I plotted the numbers, there's every number in the sequence. Do you see a pattern? Do you see that when represented this way, every term of the sequence is closer to 2 than all the terms that came before it? The terms of the sequence, one at a time, get closer and closer and closer to 2, okay? So here's what we say about that. If we can agree about that pattern, we say the sequence converges to 2. And this will be an important word for us. We'll be talking about converges for a long time, whether a sequence converges or not. I hope that with this first problem for me to tell you what that word means, it is fairly obvious. If you can see the pattern, I think you understand what that word means. All right? Okay, so I drew that picture just to help you see that. You can draw that picture for these if you want to, if it helps you. But let's talk about the wording in the bigger concept, okay? So I want to emphasize something. So there's the sequence I was just talking about. And I showed you that picture. I plotted the actual terms of the sequence on a graph so we could see them. And we said the sequence converges to 2. We may also say the same idea that the sequence converges to 2 this way. We might say the limit as n goes to infinity of this is 2. And that just says the bigger n is in that formula, the closer the number we calculate will be to 2. All right? So, yeah, I mean, the bigger the n is, then the closer the number is to 2. All right, it is a limit. Can we agree that it's a limit? Can we agree that for me to say that these individual numbers get closer and closer and closer to 2, the further down the list I go, what happens as you go this way? N is going to infinity, right? As you go down the list, the n is getting bigger, but the term is getting closer to 2, all right? So think of it like that. That n, that's the term number, that's where it is in the list, okay? And then right here, that's the actual term. All right, yeah, so as you go further down the list, the terms you see will get closer to 2. All right, I think I probably said that in enough different ways, but we'll say it either way. We might say a sequence converges, or we might say that the limit as n goes to infinity is whatever number it is, okay? All right, now that's the concept and the notation. Let's look at another one. See this one right here, 3 times n plus 1 over n plus 2 times negative 1 to the n power. That's the formula. It's not too hard to calculate the terms. And here I calculated the terms. I did some rounding this time. And you see the decimals. But, you know, that might not look like anything to you. All right? You might not see a pattern there. I don't know. So just in case, I plotted them again. First term, second term, third term, fourth term, fifth term, sixth term. You get the idea. Is this like the last one? Okay. Does the sequence converge? Do the terms of the sequence get closer and closer and closer to some number? And say, no, they don't. I mean, it's up here, then it's down here, then it's up here, then it's down there. No, this one does not converge, all right? If a sequence converges, it will look something like this. Every single term is closer to something than all the terms that came before it. That is not true with this one, all right? So what we say about this sequence is that it diverges, and to say it diverges means it does not converge. We would also say the limit as n goes to infinity, an does not exist. The terms themselves don't individually get closer and closer to any specific number. All right. So I guess you could say that, yeah, there's still a pattern. The terms oscillate between -3 and 3, but the terms themselves are not getting closer and closer to any particular number. All right. So can we accept that this one diverges in contrast to this one which converges? All right. So you see what converge and diverge both look like. All right. Okay. So let's get a little bit finer point on how we're going to do this. How can we tell if a sequence converges? Well, you can do what I just showed you. Calculate the terms and draw a graph. You know, seeing it, the pattern might be obvious to you that way. That's why I showed you those graphs. But another way to tell is just to calculate this limit directly. And if you're in Calculus 2, you've seen limits before, all right? It's something that we could review. I can make a detailed video about calculating limits. You know, if that's what people need to see, you'll just have to tell me. But we can do that limit by a table. For these particular problems, we might use L'Hopital's rule occasionally. And maybe I'll give you a formula that is for that specific limit, okay? So now I'm not going to do the graphs anymore. If you want to do that, that's fine. You can do that. I'm going to try these methods and calculate that limit directly. If that limit is equal to a number, it's telling me what the terms look like as you look further down the list. If n goes to infinity, I'm looking further down the list, right? Because n is the term number. All right, so let's look at some examples. I want to do this one by a table. Does this sequence converge? Okay, well, let's see. First term, so okay, it's 1 plus negative 1 to the n power over 2. First term, 0. Second term, 1. Third term, 0. Fourth term, 1. Fifth term, 0. Sixth term, 1. All right. Do the terms get closer and closer to anything? Doesn't look like it to me. I don't see that the further down the list you go, that the terms get closer and closer to any specific number. What does a n approach? Nothing. The terms don't get closer and closer to anything. All right. Can we agree? The limit does not exist. There is no limit to that. All right. As n goes to infinity, an doesn't go anywhere in particular. So does this sequence converge? Well, if this limit had an answer, if this was like 1.8, 1.9, 1.99, 1.999, we could say, look, every term is getting a little closer to 2. The further down the list you go, the terms get closer to 2. That's not happening here. So that's our limit. There isn't a limit, so this one diverges. Okay, so that'd be our final statement. Does it converge or not? No, it doesn't converge. It diverges. All right. Okay, so let's try this one. Does this sequence converge? Well, to find out if this sequence converges, I could make a table like the last problem. It might be easy enough for you to do that. It would be more proper to do this, though. Okay, if I was going to do this limit to explore whether this sequence converged or not, and that n going to infinity is just saying I'm looking way down the list to see what's there. Okay? All right. I'm going to see that if the terms are getting closer and closer to what as you go way out there. So here's what we'll do with this one. This one is of a particular form. Okay? As n goes to infinity, 4n plus 1 will go to infinity all by itself, and 3n minus 2 will go to infinity all by itself. That is a type of form that we can apply L'Hopital's rule to. This is considered an indeterminate form. Okay, so what is L'Hopital's rule and when can you use it? First of all, we use L'Hopital's rule for the indeterminate form infinity over infinity. There are other indeterminate forms, but this is the one we have right now. L'Hopital's rule is very easy. It says if you have that form, you can reapply your limit to the derivatives of these individually. So what's the derivative of 4n plus 1? It's 4. And what's the derivative of 3n minus 2? It's 3. So as n goes to infinity, what happens to 4/3? Well, 4/3 is constant. It's always 4/3. N can go to infinity, and 4/3 is going to be 4/3. So our limit there is 4/3. Okay? All right. What that says is, if you wrote this sequence out term by term, and you've seen me do that, right? I can write a sequence out one term at a time. Okay. If I write this sequence out term by term, way down the list, you'll see 4/3. Okay? The terms, as you keep going, will approach 4/3. They'll get closer to 4/3, one at a time. So this one will converge to 4/3. And then you could verify that by writing the numbers down and seeing that, yeah, they're going to get gradually closer to 1.3 bar. That's what that number is. Okay, So this limit I did by L'Hopital's rule, and I got a number, so that's what the sequence converges to. All right. Verify it if you want to by drawing a graph or making a table or whatever you want. Okay. All right. So let's try another one. What about this one? Does this one converge? Well, so let's do like this. I'll set up this way. If I can find this limit, then I'll know if it converges or not. Okay? Let's do a little simplifying. There's a rule for logarithms where I can take that exponent and put it there. Okay? Now, is this like that last problem? If n goes to infinity, where does 4 natural log of n go? Well, for logarithm, the larger this number is, then the larger the logarithm is. It goes to infinity. And if n goes to infinity, then, the larger n is, the larger it's going to be when you square it. That goes to infinity too. So if n goes to infinity, these will individually go to infinity. All right. Now, let's use L'Hopital's rule. This is an indeterminate form. We can use L'Hopital's rule for it. So, say, what's the derivative of that thing on the top? 4 times 1 over n. And what's the derivative of this? 2n. What happens as n goes to infinity here? Well, let's do one more act of simplifying. This, if I work out the fractions, is 2 over n squared. Am I right? I got a 4 over a 2, and I've got 1 over n divided by n. All right, so what happens to this as n goes to infinity? Well, I got 2. What's 2 divided by 100 squared? What's 2 divided by 1,000 squared? The bigger the n gets, the closer this is going to get to 0. Okay? The larger number you divide by, the closer your answer will be to 0. That's the way division works. So yes, way down the list, you're going to see 0. As n goes to infinity, you're going to see 0. If you wrote these numbers down one at a time, way down there, you're going to practically see 0. So yes, it converges to 0. A sequence will converge to whatever this limit turns out to be. All right? Okay. So I hope I've tried to get that across to you in every way I can think of. It might be worth stating that when we do this, okay, it's just allowing us to look way, way down the list, right? A sequence is a list, and that's what we're seeing way down there. All right, that's one way you could think about it. So, okay, now I said that, let me see, whenever I started telling you about how we're going to do limits, I said you can use the graph, like I showed you that. We can make a table to do the limit. We can use L'Hopital's rule, so I've showed you both of those. Maybe let's look at some formulas, okay? So there are lots of formulas I could give you. Here's a few that I think we'll run into. All right. Limit as n goes to infinity, a to the n power is 0 if a is somewhere between -1 and 1. Limit n goes to infinity of the nth root of a number is 1, as long as that number is positive. A will be a constant here. And then there's this one and this one. All right. Okay, so we'll worry about factorials in this one later. Well, actually, maybe let's do this one now. See this one right here? Let's see. Let's do this. Okay, that one. Does the sequence converge? Well, okay. One way I can figure out if it converges, remember, is to calculate this limit. Right? And if I can find the answer to that, I'll know. it's like writing these numbers down one at a time to see if they gradually get closer to something. That's what this is doing. Now, that looks a lot like this. Not exactly. It looks a lot like it. I've got something in here with n, and it's all raised to the power n. That's what this is. 1 plus a constant over n raised to the n power. N's going to infinity. Okay, so I think it's kind of like that, but I need to do a little work to simplify. Like, doesn't this split up like this? Would that be correct? That would definitely be correct. Why? Well, because if I was to write it this way, I would have two fractions with a common denominator that I could add together, n plus 4 over n. I can take it back apart, like this. So what is this? 1 plus 4 over n. Okay. Now I've got it. You see that right there? I have, look at this. 1 plus 4 over n to the n power as n goes to infinity. The limit is e to the a power. See that constant right there, a, e to the a power. That's for any constant a. So that's what I have. All right. And so this is e to the 4th power. Whatever that number is. I mean, well, I might as well tell you. So e to the 4th power, that turns out to be about 54. So if you were to write these numbers out, you know, one at a time, they'd be getting a little bit closer to this. That's what it means to converge, right? You could do that. You could look at the numbers. You could make a table. You would be able to see that. But that exact number that those terms approach is e to the 4th power. So let's say, does it converge? Definitely. It converges to that number, whatever the result of that limit is, e to the 4th power. Okay? All right, so this time I used a formula. What about this one? Well, okay, so I think this one I can use a formula also. See this 0.4 to the n power? That's like this. I've got a number somewhere between -1 and 1 raised to the power n. 0.4 to the nth power. So when we do this, then that top part is going to 0. Okay? So this is going to look like 0 over infinity. Now, I'm not saying like literally that's going to be infinity. We're just saying it gets bigger. But that top part is going to 0. That bottom part is going to infinity. And 0 divided by infinity is not an indeterminate form. 0 divided by infinity is 0. It's a determinate form. All right? So yes, 0 divided by infinity will be 0. That's our limit. So you'll find that this one is going to converge to 0. Okay? Keep writing those numbers out. Write the list. Every term is closer to 0 than all the terms before it. Okay? All right, so we can take that to the bank. 0 divided by infinity is 0. We'll get the same result if that was n squared, if that was 2n plus 1. You know, whatever that is, if that goes to infinity and this top part goes to 0, that will be our ultimate limit. All right? Okay, let's look at a few more. So let's see, let's do, okay, does this one converge? This one had the factorials in it, so I wanted to address factorials a little bit. So this is kind of like, I don't know, let's say like 4 factorial or 3 factorial. It's kind of like that, okay? This number on top is 1 bigger than that number on the bottom. Here's an example of what that would look like. Like say if n was 3, that would be what you got. That's the third term. But I want to talk about what factorials are and how you can reduce them. So 4 factorial is 4 times 3 times 2 times 1. It's pretty simple. That's what a factorial is. Multiply from this number consecutively down to 1. All right? And 3 factorial is 3 times 2 times 1. I'm going to say multiply down to 1. Obviously, you can omit the 1 because 4 times 3 times 2 is the same as 4 times 3 times 2 times 1. Anyway, so that's what factorials look like. Now, once you write it out, I see, well, it's pretty easy to reduce them. Like the 3's cancel, the 2's cancel, the 1's cancel. It turns out that that's just 4. 4 factorial over 3 factorial is just 4. So, this is going to be what? What's n plus 1 factorial? N plus 1, I don't know what that number is, but here's how it would work. Like, you take n plus 1, and what's the next number down from n plus 1? The n, okay. And then what's the next number down from that? N minus 1. And then you keep going, right, until you got to 1. All right. And then what's n factorial? Well, I don't know what n is, but you take n, and then what's the next number down from n? That'd be n minus 1. And what's the next number down from that? That'd be n minus 2, or you just keep subtracting 1. That's what that would look like. See, the same canceling happens. N minus 1, I didn't write the n minus 2, but that would be the next one. Everything from here down is going to cancel, and we're just going to get what? N plus 1. Okay? Do you think a sequence like that's going to converge? What's our sequence? What's the first term of the sequence? 2. What's the second term of the sequence? See, 2 plus 1, that's 3. 4, 5, 6, 7. Okay. Does that converge? Do these numbers get closer and closer very gradually to something? No. I can say that the limit as n goes to infinity of a n, which ultimately reduces to that, is infinity. Okay, so that's not a number. If that limit was 5, I would say it converged to 5, but infinity is not a number. That just says that the terms of the sequence get bigger and bigger. So does this one converge? It does not. So we'll say it diverges. But along the way, I showed you what factorials are, how we can reduce them, and we can understand that limit. That's probably not too far out that you can see that the limit of that or this as n goes to infinity is infinity. Okay? All right, so let's look at something different. Find a formula for the nth term of this sequence. So here I have the list. I don't have the formula. So I'm thinking like a n equals what? What formula produces that list of numbers? Now, you could just take a random guess at this and try to figure it out by trial and error. You can do that. But this sequence has a pattern to it. It looks like every term is the term that came before it plus 7. So when I'm looking at this one, I want to find a pattern. All right? So can we both look at this and say, yes, there's at least a pattern there. Any term plus 7 gets you the next term. All right? Now we might as well learn what that's called when you see that kind of pattern. It's called an arithmetic sequence. Okay? It takes this form. Any term plus some number d, which is fixed. In our case, that number appears to be 7, gives you the next term. That's exactly what we have. The formula to produce that list is that the nth term is the first term plus n minus 1 times d. So that's what we have. It's arithmetic. And I can say d is equal to 7. Any term plus 7 gets you the next term. What was the formula for the nth term? an is a1. a1 is the first term plus n minus 1 times d. Well, I know the first term. And d7, I can put the rest of it together, so here we go. an is the first term, negative 4 plus n minus 1 times d. Isn't that what it said? Yeah, that's the formula. That will do it. Let's do a little simplifying. an is negative 4. Let's go, why not? We can put some terms together. So plus 7n minus 7. So here will be my answer. an is negative 11 plus 7n. Okay, let's try it out. Let's make sure. So what does this say the first term is? I put 1 for n. What's negative 11 plus 7? That would be negative 4. What's the second term? I put 2 for n. What's negative 11 plus 14? That's 3. Let's do one more. What's the third term? The third term I would let n be 3. So that's negative 11 and 21. Negative 11 plus 20. That's 10. It works. All right. But, you know, just to make it a little easier, I told you what kind of sequence it was. All right. So when you see problems like this, we'll try to find patterns. And if we notice it's an arithmetic, then I have a formula for you. Okay. All right. So let's try 2 more of those, and then we'll be done. So can we find a formula for this? And can we find a formula for that? Okay. Now, these 2 are not arithmetic. They're not like the last one, but they still have patterns, and so we can probably figure it out from the pattern. Like this one, 2, 4, 8, 16. Those are powers of 2, right? 2 to the first power, second power, third power, fourth power. I see a pattern. 3, 9, 27, 81. 3 to the first power, second power, third power, fourth power. I see a pattern. Well, that one wasn't too bad. 2/3 to the nth power. Isn't it true that this formula would replicate that list? Let n be 1, 2/3 to the first power, 2/3. Let n be 2, 2/3 second power, 4 over 9. Let n be 3, 2/3 third power, 8 over 27. It works, all right? Okay, so, you know, I got that right from looking at the numbers. I just think with this one, the pattern was really obvious. You might notice some of them are like that. What about this one? This one's less obvious, but so I think we can do it though. Plus, so 2 patterns are going on. Plus, minus, plus, minus, plus, minus. Okay, so the signs alternate between plus and minus. And on the top, I see 1, 2, 3, 4, 5. On the bottom, I see 2, 3, 4, 5. So I'm thinking like this. AN equals n over n plus 1. Would that work? Let's see. So if n is 1, I'm going to get 1 over 2. Okay, check. If n is 2, I'm going to get 2 over 3. Check. Okay, so it works. Oh, one more. Okay, if n is 3, 3 over 4. Check. Okay, it works. What about the signs jumping from plus to minus? How am I going to do that? Maybe multiply by negative 1 to the n power. Is that going to do it? So this will get me a half, 2/3, 3/4, 4/5. Does that change the signs the right way? What's negative 1 to the first power? What would this make the first term be? 1 over 2 times negative 1. We don't want to be negative. What's the second term? Negative 1 squared. It's going to be positive. We want it to be negative. All right, so that's not going to work. How are we going to fix this so that it gives us plus, minus, plus, minus? Well, we could just shift the exponent like that. That'll do it. What's the first term according to this? What's the sign of the first term? Put 1 in for n. Negative 1 squared. That's positive. For the second term, put 2 in for n. Negative 1 third power, negative. That will do it. All right? So there was a pattern, but it may take a little trial and error to fine-tune this so that it gives you that. What makes this right is if it produces exactly that list up there. And that formula will do that. Okay? Let's look at one more problem then. Here it is. This one looks like a real mess, but look at that recursive sequence, all right? This one's so complicated, it was hard to write down, but it's okay. It's root 12, and then it's root 12 plus root 12, and then it's the square root of 12 plus root 12 plus root 12, and you can kind of see a pattern to it, but it looks like a mess. Dot, dot, dot. It goes on forever. Those are the ellipses. So, 2 things. Can you find a recursive formula for this? Okay. And then the second thing is, does it converge? And I'm going to just ask you to use a table for that. Well, okay. I can see a pattern to this. Here's how I'm going to try to get you to see the pattern. See how that is right there. Okay. And see how this is right there. Okay. And see how this is right there. All right. I had to draw on it to try to get you to see the pattern, but it looks like you can find the terms this way. So any term is the square root of 12 plus the term that came before, right? Like, is this one the square root of 12 plus the term that was right before it? It appears to work. All right. So that's what I want for this one. And I want also to say that the first term is root 12. Remember, for the recursive sequence, I can't just give you this, because if you didn't have those up there and you didn't know the first term, there'd be no way for you to use that to find any of the terms. But if I tell you, all right, the first term is root 12, then that says the second term is root 12 plus root 12, and that's true. And then you can find the third and the fourth from that. Okay, so there's our recursive sequence. We might also say something like, obviously, I can't put 0 in there. I got to start with 1. So that n has to be greater than or equal to 1. So we'll also say something like that. Okay. All right. Let's do this next. For the converge part, I'm going to leave some of this to you. But if I'm making a table, then it's just going to be a matter of calculating those numbers. All right? Okay, so let's see. We'll do n here, and we'll find an like this or like that. Okay? So we'll do 1, 2, 3, 4. I think 5 will be enough. Now, I want you to actually do the calculations. But you'll find that these numbers pretty quickly and obviously are going to 4. All right, I'll let you do the math, but that's what you'll see. It will be pretty obvious in the table. All right, so you're going to calculate those numbers, but that's what you're going to find. So we'll say, yeah, this one, does it converge? It does. It converges to 4. All right, that's kind of an informal way to figure out by the table, but it's one that is obvious enough and accessible to you. All right. Okay, so I did 2 things with this one. I had to find a pattern and all that up there. I used that pattern to give a recursive formula. That's this. This will reproduce that exact sequence onto forever. And then I figured out by calculation, by the table, that it converges to 4.